The plan is to complete the normal distribution plus hypothesis testing. I actually would like to tell you a little bit more about the variance operator. And I want to conclude with two applications. So, police and crime, and cholera. So we're going to try and explore this idea of why do we observe, for example, a lot of the times if you look at the data and you look at presence of police and crime, they are negatively or positively correlated? Positively correlated, right? Which might lead you to believe that the more police that there is around, right, the more crime there is, right? Maybe you come up with some story that police are actually helping crime, right? So what sort of methods can we use in order to try and establish some form of causality, right, rather than correlation? So anyone can explain why you would expect a positive correlation between crime and police? Yeah.
The police will register the crime?
Say it again?
The police will register the crime?
Okay, here's a good point, okay? It might not have nothing to do with actual crime, right? You have to realize that that positive correlation is coming due to registered crime. If the crime was not registered in the first place, right, the presence of the police just facilitates registering of the crime. Okay, so that's an excellent point. But why else? Why would you expect a positive correlation between the two? Yeah.
In areas with more crime, we put more police.
Exactly, right? So there's that channel as well. So in areas where you expect more crime, you'd put more police, right? Now, the question that you should really ask yourself is, in the absence of police, if I was into this like different world where there was no police, what would have been the crime rate, right? And that's how you would have ideally established causality. And what that application does is try to answer exactly that question through what's known as a natural experiment. And we're going to take the case of Argentina and Buenos Aires. There was some terrorist attack towards the Jews, and that led to a very nice natural experiment. And the second application is cholera. So for a very long time, we were not sure whether cholera was airborne or was waterborne, right? So we didn't know how to. So you might have kind of seen those movies where they go into this cholera infested places and they cover their mouth, right? Because they might have thought that it was airborne. And I'll show you an application again of similar statistical tools that provides relatively strong evidence that cholera was not airborne but was waterborne. And again, we'll look at one example from London this time. Okay? So these are the exciting bit and applications, but in order for you to be able to do these nice applications, you need to build the abstract modeling that goes behind those applications. So let me go into this normal distribution. So far, what you know is that if a variable is normally distributed, you will be given its expectation, or mu, and you'll be given its variance. For example, I can call that sigma square. So this is variance, this is expectation, or mean if you like, and sigma is just the standard deviation. Standard deviation. Okay? Now let me give you an exercise. Let's go straight to an exercise. Imagine that for whatever reason, let's put some context into it. You are a producer. You produce chocolate chips, for example, and you put them into a bag. Okay? And you have a machine that needs to be calibrated into how many chocolate chips puts into each bag. Okay? And let's say, for example, that the chocolate chip that it puts into a bag. Of course, it's not the same all the time, it changes. And let's say that it's normally distributed, okay? It's normally distributed, and you know that the variance is 1, or the standard deviation is 1, right? But the machine, once in a while, stops being calibrated, okay? So it either gives you more chocolate chips on average or less chocolate chips on average, right? So when the machine is not calibrated, you actually go on and say, well, actually, I don't know what this average is, okay? And let's say that you would want that average to be, 100. Okay, this is the ideal, okay? So let's say that you have these machines, they never falter on the standard deviation, okay? So you know the standard deviation is 1, okay? And let's say that this is 100 gram, okay? So you want sort of like 100 gram worth of chocolate chips. But you don't know whether the machine is calibrated or not, okay? How do you go about figuring out whether the machine is calibrated or not? Let's talk about it informally. And of course, you don't want it to be more than 100, and the reason why you don't want it to be more than 100 is that you're wasting. Right? You don't want it to be less than 100 because then you're false advertising. Right? You're saying there's 100 gram in there, right? So you want it to be very close to that 100 gram. So how do you go about figuring this out? Sample testing. So what would that involve? Okay, so maybe take every 10th package that comes out and measure it. Okay, that was arbitrary to take the 10th one. How many should I take? Would 1 suffice? Maybe 100? Where do I stop? Where do I decide whether 100 is a good number, 1 is a good number, or 10 is a good number? Well, that's where good old trade-offs come in again. Right? Of course, the bigger the sample is, the better it is. And the reason why it's going to be better is because your results are going to be more precise. Okay? But of course, the bigger the sample is, the more costly it's going to be for you to take over that sample. And in statistics, generally, we're not satisfied with, I'm going to take 10 of them or 20 of them, and I'm going to get a feeling of whether it's right or it's wrong. Okay? In statistics and in hypothesis testing and in the courses that you're going to see during this program, we will formalize this idea of, I don't know this average. If I take a sample, how do I go about testing this hypothesis, whether it is calibrated or it's not calibrated? So imagine that, let's kind of have a setting here. Your H0 says mu is equal to 100, i.e. the machine is okay. I don't have to worry about it. I don't have to adjust any of it. Your H alternative, your alternative hypothesis, your alternative view of the world might be that mu is different from 100, i.e. I need to adjust the machine. Okay, well, let's think about what your colleague here kind of started off with. Imagine that I take a sample of 10 observations. Okay, how would that sample look like? Well, it would look something like this. x1, x2, all the way to x10. Okay, and what I could do is I could do something like a sample average. So I could do mu hat. Hats will generally be used in this course to indicate things that are sample, that belong to a sample, but not necessarily to the population. So this will be, let me use my sigma notation, sum I going from 1 to 10 of what? Of xi, of course, right? Because every single one of this is a different observation, is a different measure of that machine, divided by 10. Okay? Now, you can bet with certainty that that sample average will never be 100, or it will be 100 with probability 0. Now, note what I mean by exactly 100. By exactly 100, I mean 100.00000000000 to infinity, right? So you can, the moment you see it that way, and the moment you realize that this chocolate chips might be continuous, you realize that the probability of you getting exactly 100 is 0. So we need something a bit more formal, and we need something a little bit more relaxed at deciding whether the machine is okay or the machine needs fixing or needs adjustments. So how do I go about that? What's the first thing that I should try and figure out? Yeah.
Sort of acceptable range.
Acceptable range, but in order to build that acceptable range, what do I need to do? In order to build that acceptable range, what do I need to do? What would I need to know? You can do something informal and say, well, my acceptable range is between 100, 100.1 and 99.9. And you can just do that informally and say, I'm happy with that. And that's how most people might do it. Yeah.
You have to decide how much you want to give up on your certainty level.
Okay, if we want to be a bit more formal, right, it's all to do with this idea of range. You need to figure out what is the distribution of this. Your first step is to figure out what's the distribution of it, right? Under the H0 hypothesis. So you might want to figure things like this. If H0 is indeed true, what is the distribution of mu hat? Well, here's a couple things that we need to know about it. One, that's an important observation, okay? For now, just take it at face value. What I'm saying is, every single one of these xi's, every single one of these is coming from this normal distribution. So x1 is normally distributed. It's coming from a normal distribution. x2 is normally distributed. My mu hat is a sum of these normally distributed variables. Take it at face value that whenever you sum normally distributed values that are independent of one another, you will also get a normally distributed value. Okay? So that's an important thing because it's already saying something like this. Mu hat is normally distributed with some unknown mean or average and some unknown variance. Well, that's useful to know that this is normally distributed. Of course, what is your next question? What is your next question? Remember, we want to find the distribution of this mu hat. What should be your next question? If H0 is true, right? Assuming that H0 is true, what do I expect this first question mark to be? 100. That's right. So the second point that I would need to do is if H0 is true, what is the expectation of mu hat? Well, here is some, again, I will not have time to fully describe all the properties of expectation, but expectation is a linear operator, so you'll have expectation of x1 plus x2 plus all the way to x10. divided by 10. Constants can be pulled out, so you're going to have 1 over 10 expectation of x1 plus x2 all the way to x10. And then you're going to have 1 over 10. Because it's a linear operator, I can do things like expectation of x1 plus expectation of x2 all the way to expectation of x10. This might seem a little bit fancy, but all I'm saying is that if you have two variables that are both average at 5, okay? You have one variable at 5 and one variable at 5. If you take some observations from this pile and some observation from this pile, and you do the average of that new pile, the average will be 5. What if you take a variable that has an average of 5 and a variable that has an average of 10? Right? If you do the average of those two, you will get 7.5. That's all that thing is telling you. Okay. So then, what's the expectation of x1? What's the expectation of x1 under the h naught? 100, of course. What's the expectation of x2? 100. So each of those individual expectations is exactly 100. So what you'll have is 10 100, 10 times 100 divided by 10, this and this will cancel, would be 100. So don't forget this red thing in red, right? We are assuming that h naught is true. So if h naught is true, things are becoming a little bit more known. So this thing here now is 100. Okay, this is good. Remember with range, he was talking about finding ranges of stuff. What you would want to know is what's the probability of being within a particular range, right? How likely it is that I'm going to be within that range if the h naught is actually true. So everybody with me? So here you're going to have to use what we learned yesterday about normal distributions and the likes. But before you do that, you will absolutely need to know what this is. If you don't know what the standard deviation is, you'll have no idea whether that range is large or whether that range is small in probabilistic terms.
I was going to say, can you zoom in a
Yes.
little bit? Because it's really hard to see all these small things. Thank you.
Is it better? Okay. You can also blame my handwriting. Right. So the third question and the final question that we need to kind of answer this is what is the variance or standard deviation of mu hat? Well, here, before I proceed to figuring this out, I want to give you what I initially promised you, more about variance operator, okay? So if you think about it, this is all you need to know about expectation operators. So if I were to kind of put this into rules, what I've done here is I've told you that the expectation of a constant times a variable is just the constant times the expectation of the variable, okay? If I do this bit here, the rule is that the expectation of a variable plus another variable is simply the expectation of this plus the expectation of this. Okay? That's all that it is. So those are the two rules that you need for expectation. Now to talk about variance, I'll have to give you some rules. Anyone can tell me what is the variance of a constant times x? C squared variance of x. If you go back to the formula of variance, that would become very obvious. Okay? If you multiply a variable by c, what happens to its average? Also gets multiplied by c. Okay? What happens to each individual variable of that? Also gets multiplied by c. But the variance squares things. So one rule here is that this is going to be c squared times variance of x. Okay, that's one rule. Okay, second rule. What is the variance of x plus y? What is the variance of x plus y? Well, you have no way of knowing this if you haven't seen this before. But it will happen to be variance of x plus variance of y plus 2 covariance of x and y. Okay, that's another important formula that you ought to know and understand. Now let me try and give you some context into it. I actually never remember this formula. I don't remember this specific formula because it's actually useless the moment you go to like 3 variables, for example, like x plus y plus z, or 5x plus 7y plus 25z plus some other variable. But here's what I remember, and here's how I usually deal with any sort of variance operators. I think of this as covariance of x plus y and x plus y, right? Remember that the covariance of the variable with itself is the variance, okay? The moment I think of it this way, I can then list all the items and put them into a matrix. So I take all of these items, 1 term, 2 terms, 1 term, 2 term, they're all going to be the same. I put them into a matrix. So it looks like this, x, y, x, y. And inside here, I take the first term and the second term and I say covariance xx, covariance xy, covariance yx, covariance yy. And I know that this covariance here is equal to the sum of all the terms in the matrix. So I know that this is equal to, what's covariance of x with itself? Variance x. What's covariance of y with itself? Variance y. What's covariance of x and y, and how does it relate with covariance of y and x? The order doesn't matter, so I can switch them around. So this will be equal plus 2 covariance of yx, if you like, or xy, doesn't really matter how you call it. So let's say I gave you another exercise. I gave you something like, what's the variance of 3x plus 2y plus 7z? My immediate reaction to this is that some people have learned the formula how to deal with 3 variables. I never can remember that formula, and I don't care. So the way I would do is I would go and list all the terms, put them into a matrix, 3x, 2y, 7z, 3x, 2y, 7z. And then I'll go here, covariance of 3x, 3x. Note that everything on the diagonal would be of the same thing. Covariance of 2y, 2y. Covariance of 7z, 7z. Okay? So everything on the diagonal is going to be variances. Agree? Everything on the off diagonal is going to be covariances. But the other thing to notice is that this thing here is going to be the same as this thing here. This thing here is going to be the same as this thing here. And this thing here is going to be the same as this thing here because it's symmetric. So here you have a formula for how to find all these variances and covariances and the likes and how they're related to one another. So let's try and apply this to our problem. So actually I'm just going to try and get a slightly bigger handwriting. So what is the variance of mu hat? Well, it's the variance of x1 plus x2 plus x10 divided by 10. If I take the 10 out, how should it be taken out? 1 over 10 is a constant, so if I want to take it out of the variance, I go to the first rule, and the first rule says take it out with a square. So it's going to be 1 over 10 squared times variance of x1 plus x2 plus all the way to x10. Now, here's something that is actually very useful here. All these events are independent of one another. So how many chocolate chips were produced on that first shot is completely independent on the second one, the third one, and the fourth one. By assumption. It didn't have to be that way, but that's what I'm assuming. So what's going to be the covariance of all these terms? if they're independent? 0. Which means that your job is very easy, because the variance of all of this will just be the sum of the individual variances. But what's the variance of x1? Sigma squared. What's the variance of x2? Sigma squared. What do I mean by sigma squared? I mean the original number that I gave you here, which is 1. Because you know, I told you this machine never falters on standard deviation. Its standard deviation is simply 1. So what's the standard deviation of that first observation? 1. What's its variance? 1, or 1 squared. So what you will have here is variance of x1 is 1, variance of x2 is 1. What's the sum of them? It's 10 times 1 over 10 squared. This cancels with this, so you get a variance of 1 over 10. Let's take a different color, and I'll give you some time to discuss this with one another, okay? If I'm a bit lost on this, it's okay. I'll give you a bit of time to discuss this. What would happen if you change this from 10 to n? What would happen to all these calculations if instead of 10, you had n here and you had n here? Well, 1 over n will come out as n squared. This top bit here would have been n times sigma square, okay? So this whole thing would have been sigma square divided by n. What you should be able to see is the benefit of having a larger sample. The larger that sample is, the smaller the variance of your estimator. In other words, the more precise it will be. What happens as this n gets extremely large? The variance is pretty much 0. Which means, if I went to that chocolate chip thing, right, and I did 1,000 draws, I would be fairly sure that I'm very, very close to whatever that average is. So if I got like 103 out of 1,000 observations, I'll be very, very sure that that machine needs adjusting. Right? So that machine needs adjusting. Right. 5 minutes. See if you can discuss it with one another. Come up with questions, help the people around. Okay, let me take some questions. We're not done yet, by the way, but I just want to make sure that you're following up to now. So, what are your questions? Yeah.
You scroll up a little bit
Yeah.
to the
Tell me where to stop.
there next. Well, that's where I wanted it. But
Okay. Do you have a question, or you just wanted to?
I wanted to see the.
Okay.
was it red?
There was a question here, I think. Yeah.
Could you please clarify which are the rules and which are the assumptions that we're making? Because
Ah.
I don't know a lot.
Right. Okay, that's a good question. The assumptions, of course, are this on the distributions that I'm making on the x, okay? So here, I'm assuming, this is an assumption that I know that this machine produces normally distributed chocolate chips, and I could also add here independence. IID sometimes is called, that this observation are also independent of one another. That is also an assumption, okay? This circle here is really the assumptions that I have about this x, okay? That's all that I have. And of course, I am assuming that I know what 1 is, that variance is equal to 1, okay? Now, the other question is, what are the rules? Well, the rules are things like here. Going from this position here to this position here, I don't need an assumption. These are just expectation rules. So the moment I tell you an assumption about x1 and x2 and x10, I told you every single one of them is normally distributed. Okay? Then from here all the way to here, you don't need assumptions. You just need the rules of expectations. Everybody is with me? Of course, here I'm also making an assumption. What assumption am I making here? That the mu that I don't know is equal to 100. Or in other words, I am further assuming that H0 is indeed true. Okay? So, remember what my H0 was? That mu is equal to 100. If I didn't assume that, of course, I could not write 10 times 100 here. I would have had to write 10 times mu. And this answer here would have just been mu. What allows me to say that this answer is 100, I'm saying, let's assume the machine is okay, doesn't need adjustment, and it gives you exactly 100. What's going to be the average of this measure, which is the sample average? It's going to be 100. What's another rule? Well, these are rules. These are not assumptions, these two things here. I don't have to assume that variance is equal to 1. That's just a property of variance. So when I go from here to here, I don't need an assumption. It's a rule. These are variance operator rules. Okay? That's a very good question. Feel free to ask these clarifying questions, okay? Because you might think like, maybe I'm a bit behind, but they're actually very useful. And and they're very useful to me as well, right? Because a lot of things I just take for granted just because I've been doing this for so many years. Yeah. Yeah, tell me where to stop. Okay, more questions. Is everybody with me? So remember, yeah.
You said before that the variance of x1 y1 to bottom is equal to 1. Why is that?
Because that's another good clarifying question. because I told you that every single one of those x's is normally distributed and it has a variance of 1. Okay, this is not a rule. Again, it's part of this assumption here. I assume that every single one of those observations will have a variance of 1. Okay? My focus is not the variance because I've just given that to you. My focus is the mean. And I made up this example of this machine that is always known what the standard deviation is, but you don't know what the mean is. More good questions. Okay, everybody's with me? Now, the moment I have these ingredients here, look what I have so far. If I assume that xi is normal mu1, then for a sample of 10 observation, I know that mu hat is also normally distributed with mean mu and variance. What is the variance? 1 over 10. Okay? This is my initial assumption. That every single one of those draws or observations come from this distribution. And from there, using the rules of expectations and variance, I can come up to this. If on top of this, I add to this plus the fact that h naught, which says mu is equal to 100, is true, then I can further write that mu hat is 100. The h naught allows me now, I fully know this distribution of this. I can graph it. I can graph this, right? What do I know about the normal distribution? It's centered around 100, so I go and draw a graph. It's centered at 100. And I'm going to make the graph a little bit bigger than it ought to be. This is 100.1. Well, actually, we'll take the square root of that, but which complicates things a little bit. This is 100 plus 1 over 10 square root of it. This is 100 plus 2 over square root of 10. What am I actually doing here? I understand this is the variance. So square root of that is the standard deviation. So I'm going 1 standard deviation away from the mean, 2 standard deviations away from the mean. And really what I should have is a bell-shaped curve that kind of looks like this. And what do I know? I do know that 100 minus 1 over square root of 10. Okay. By the way, note this is a small number, right? This is roughly about 3, so this is like a third. Okay? So if you don't like these numbers here and you're a little bit like, what the hell is that? You could just tell yourself that this will be approximately 100.3, roughly. Okay? If you wanted to kind of get that sense here. This thing here will be 100.6, roughly. Okay? So what do I know? I know that if h naught is true, what percent of my observations will lie between here, between these two things here? What percent of my observations will be within this range here of 99.7? This is approximately 99.7. What percentage of my observation would lie here? 68%. I know this, you should know this. What percentage of my observation would lie within 2 standard deviations? Within this bit here. What percentage of them? 95%. Okay? Now, is it possible that even though the machine is okay and doesn't need adjustment, that you get an average of 200? Of course it is. It's possible that you get an average of greater than 200. Now the next question, which is the far more important question, is how likely it is that you're going to get an average more than 200 if the machine is okay. Extremely unlikely. You could practically say it's never going to happen. Okay? Sure, theoretically speaking, there is a probability that you could be, mind you that if you go to 200, right, you are about 100 units away, right? Which means you are about 300 standard deviations away, right? So the probability of being there, it's 0 point, maybe hundreds and hundreds of zeros, and maybe some numbers left over, right? So it's very unlikely, okay? But it's still possible. So we now need an extra term here. We need some sort of level of confidence or level of error that we're willing to make. Right? So if you get something for 200, right, you're willing to say, hey, I'm happy with the fact that I might be actually, that it might actually, the machine might not need adjustment, but I'm going to do the adjustments anyways, right? Even though there's a tiny chance of that happening. So in order to find the right range, right, so if it falls out of this range here, should you adjust the machine if it falls out of this range here? Well, it depends what your level of confidence is. There is 32% chance that it will fall out of this range even though the machine is okay, and you shouldn't do anything about it. Should you adjust the machine if it's within this range here? So if it's between 99.3 and 100.3, sorry, 100.9. Should you do anything within that? Well, there is a 5% chance that if it's outside that, the machine still doesn't need any adjustment. So the question is, where do you stop? And the answer is, it's subjective. It's up to you. Okay? So if you are happy of adjusting the machine where it doesn't need adjustment 5% of the time, then anything outside this range should lead you to adjustment. Okay? Anything outside this range should lead you to adjustment. So we're going to call that significance level. So sigma, I'm going to call this as significance level. My screen froze. Significance level is the probability of rejecting H naught, i.e. adjusting the machine when the machine is okay. In exceptionally creative term, this is called type 1 error, which means nothing to me. Right? So this is like saying this significance level is all that you need in order to complete your hypothesis testing. All that you need. Let's recap. Let's take, for example, significance level is equal to 5% in our case. So let me go back to my assumptions. at the top here. So let me add this extra assumption that my significance level is 5%. This is my significance level. Now, remember what we started off with? Maybe we take a sample. What should be the range? We kind of don't know. You're kind of hand waving a little bit on what we do and what we don't do. And under these assumptions, we don't have to do hand waving anymore. So the moment you give me your significance level or how precise you want to be, I can make this operational. Here's how I make this operational. I figured out what my mu hat is, and I said, look, my mu hat is under h naught, centered around 100, and with a variance of 1/10. I was able to draw this, and then with my significance level of 5%, then this red bits here are my rejection areas. Rejection areas. Note, I was able to do all of this without having access to any data. Did I need the data? Did I need what x1 was or x2 was or anything of that sort? No, I didn't. So all of this was done without the need of any data. When does the data come into play? After you've done this work. So now you go to the data and you found that it is 100.1. What do? You say the machine is okay. What if it is 100.8? You say the machine needs adjustments. And that's how we formalized it. We came from something that was a bit hand-wavy to actually giving you precise ranges. Within this range here, at that significance level, you should reject the hypothesis. Is everybody with me? Maybe 2 more minutes. See if you can discuss it with one another. I'll take some more questions. We'll take a 10-minute break. We'll do 2 applications. We'll go home. Yeah, see if you can discuss it for 2 minutes. See if you can come with questions. So, feel free to get questions from different angles.
So you're okay if you're 95% sure that your range will not fall out of
Okay, let me take some final questions on this hypothesis testing, which is actually very important, okay? If you understand this well, it's kind of like the backbone of anything, and you're going to do lots of this hypothesis testing, and eventually it will boil down to the same thing. You're going to have an estimator or something like mu hat. That something will have a distribution. You will have some significance level, and based on all of those, you'll be able to figure out rejection regions and the like. Of course, it's going to be a bit more complicated because there's some adjustments that we can make to this, but the backbone is here. If you understood this, then you understand the principles behind hypothesis testing. Right? Those are the sort of like principles behind that. Let me take some questions now on this. Is everybody with me? Yeah, everybody understands the basic, or they think that they can go away and read a bit or re-listen to this lecture and maybe they'll understand some stuff. Just so that I don't forget, so there is an exam at 2 today. I will post the exam on Moodle together with the solution. So the exam will be available from 2 onwards. The solutions will be available from 4 onwards. You're very welcome to just take that at your own time. Okay, so you don't need to necessarily show up here at 2, but I will be here for those that want to take that opportunity, that 2 hours, to just take that exam. And I know some of you took that opportunity for the math side. So it's up to you whether you want to come here and just be in a quiet environment for those 2 hours and try and attempt the exam, or if you want to do it in your own time. I'm especially thinking about those people that are going to take the exemption exam, right? Because they're going to have 3 hours back to back, right? So if you're taking the exemption exam, I would recommend you just focus on the exemption exam, right? And leave this one for, I don't know, for later. Right. Let's take a 10-minute break until 1:45. 10-minute break, and then we'll resume with some applications. I try. As you know, because I don't organize. I have no idea. I would assume going through your undergraduate material of statistics to be what I would say. You'll feel less. So things like regression and hypothesis. One of the fun examples. But I don't. Yeah, I have no idea. Non sapevole dei limiti. Che non risposta. I think the best is to find I think that is the best. It shouldn't be too difficult. Go to the office and have concern on it, if they can pick out, depending on their performance, how well they've done before. I think that's the best value. Someone that's done it before, you can get someone that's very far away from the way you build stuff. I think that is the best. The best way. Yeah, I think generally that's my best recommendation. Of course, Khan Academy is also great.
Yeah, I am using it, but I feel like it's not going
But that would be my first. There is then website out there. Your best bet is to find someone who you like. And makes you like move the progress very quickly. And it's coming from the that would be
For example, this type of charger is like a long charger.
Okay. Right, so as promised, Do you know about Jon Snow?
So slow. You know nothing.
You know nothing of Jon Snow.
Yeah.
Jon Snow was a scientist, a statistician, even though most of you might know Jon Snow from Game of Thrones. But we're going to talk about another Jon Snow today. And I want to try and illustrate this very powerful method of trying and establishing causation, okay? That A is causing B, which is actually very hard to find. I have shamelessly borrowed this note from one of my very good friends and colleagues at Oxford because he's done such a good job at presenting these differences and differences. And you'll see this is actually called computer practicals because he actually does this in front of Stata and you actually get to play with the code, which is exactly what you're going to do during the year in the quant course. So you'll actually, in the classes, you're going to have to play with Stata and you're going to look at some of these things and you're going to be able to execute them. But, so Jon Snow looked at the causes of cholera in 1855. Okay? So, you had two competing theories, as I said. Either it was airborne or it was waterborne. Okay? So, it doesn't matter the names, but you had this miasma theory or germs, right? So, germs would carry out through water, or they would, the other theory, they would carry out through air. Now, there were only two water companies, or two main water companies. There was a lot of them, but only two main water companies. And they were taking the water from pretty much the same source in 1849. But in 1852, one of the two major companies decided to actually supply the water that was further upstream, where it wasn't contaminated. And then in 1954, there was another big cholera outbreak in London. So here you have it. You have an event that happens before something like this happens. This is like a natural experiment. This is one of those things that academics really long for, because there is a lot of things that you can write based on this natural experiments. Something happened that was unusual. Okay? And that allows you to ask the question, which of those two theories is more likely to be supported by the data. So, this is the original data set of Jon Snow. You could see the the population in the different sub-districts, the deaths that they had by cholera, and who was supplying the water to those bits. And of course, there's a data set. We can actually get this data set, but that's not my point. Here's my point. 1949, these two companies here, right, or these two areas here, would have otherwise been fairly similar. So the question is, look at this area here versus this area here. There's some differences, right? One is 131. This is 111. Okay, so we do notice some differences in this too. But then this that was partially done by Lambert, or at least partially done by Lambert, which got better water, in 1954, we see quite a massive reduction in the number of cholera outbreaks. So the intuition there is to say, well, look, I'm assuming that prior to this natural experiment, this improvement in the water quality, these differences in depth, at least in percentages, would have remained. Okay? They would have remained post this natural experiment. And to kind of give you a sense of this graphically, you will see this in more details in your quant course. I'm making what's known as a parallel trend assumption. You see that green line and this blue line here? These are parallel. So, but my assumption is is that these two measures would have evolved in parallel trends in the absence of this event or in the absence of this treatment. Okay, and this figure here, right? So we went to about 60-something deaths, right? This difference here is the difference in difference. Now, you're going to run into the same trouble that we did with the hypothesis testing. Is this large enough? Because of course, these differences here are only statistically similar, right? They're not always going to be the same, right? Sometimes a district is going to have more death than the others, etc., etc., even if they're similar in their differences, right? Because this difference here might be, random, will be random. So you're still going to have the question, is this difference big enough? And of course, what would you need to do in order to establish whether that difference is big enough? Same steps that we did. You need to figure out an expression for this difference in difference. You need to then say, how is it distributed? Under what assumptions will I be able to come up with this distribution? Then you have to come up with a significance level, how precise you want to be on that. And then finally, come up to a conclusion whether you want to reject the hypothesis. What was your null hypothesis? The null hypothesis could have been that water has nothing to do with it, right? If water has nothing to do with it, this parallel trend holds, you should have seen those observations being similar to that. But of course, I can always lie you with statistics, right? This difference here could be really, really, really tiny, right? I could just change the scales of stuff and make it look like it's huge. Okay. This difference could be tiny in a standard deviation sense. So here you have it pretty much. So this is the parallel trend assumption that I talked about, and this is the difference in differences estimator. So I see a reduction of 51 deaths. This is that height, that red height, and the question that you would need to answer on a more formal basis is this difference big enough or not? That's not my goal for today. Okay, I don't want to do any of that. Today, I just want to give you a flavor of this experimentation. Let me go to something that's a little bit more recent, which is the impact of police presence on car theft. So we're looking at something very, very particular. Right, so in July 1994, there was a terrorist attack on the main Jewish center in Buenos Aires. The response of the government was to increase police force near Jewish institutions, or well, the Jewish presence was prevailing. And here you have a natural experiment. You can take the areas, or anyone can think of how you would set this experiment up. You're trying to figure out police presence and car theft in this particular one. How would you set this experiment up, given your expertise with Jon Snow? How would you set this experiment up to figure it out? Yeah.
The false situation, so police presence between the difference between the police presence between districts in the city.
Yeah.
And then you see the change. So the Jewish forces then after the change, after the experiment.
What is the event? What happened? What is
more
the
police presence.
more police presence, right? It's like the chain of water supply, okay? So more police presence is the event that happened. Did more police presence happen everywhere? No, only in certain areas, right? So that's nice because it allows you to distinguish between the different areas. But what is the variable of interest? What is the variable that you're looking for? What is the variable that you're interested in? The number of partners, right? And that's exactly what you're going to do, and that's exactly how you go about this idea of difference in differences, right? So, correlation studies often find that presence is positively correlated with crime, right? Surprise, surprise, right? Well, we discussed a little bit at the beginning why that might be the case. But of course, these studies suffer from omitted variable bias and all sorts of other things. So here's a graphical depiction on this. terrorist attack, police force. I relook at the data again here. Okay? So I have a pre-event data with two different groups, and the post-event data with the same groups, but there is a different treatment on only one of the groups. And what generally happens that it's, look at this. So pre-attack, these two areas of town seem to be fairly similar, right? Even though you should be careful about that. Because you should say, what is similar? Well, in what sense is similar? Just because I have a few decimal places, that doesn't mean anything. Right? Because I can scale things up. You should really ask about, what is this difference in terms of standard deviation? Is it a third standard deviation away, or is it 5 standard deviations away? Because that distance could be many standard deviations away, or it could be just a few standard, or like a fraction of a standard deviation away. But that's outside the point that I'm trying to make. But just be mindful of this. But what's important is this, that whatever that distance is, you're here, they look fairly similar, post-attacks, areas with Jewish institution, they have a higher police presence. What happens to the theft? Well, it seems like they have, reduced by quite a bit, right, in comparison to this. So again, the parallel trend assumption, but this is really quite powerful, right? So here, now you can really make a case that actually, no, police forces, the presence of police forces at terrorist particles seems to have prevented this car theft from happening. Right, so again, the way we would do it, we would figure out whether this number here, statistically speaking, is big enough for our purposes. To do that, we'll need to assume things that allows us to say something about the distribution of that number. And again, difference in difference explained. You can see here how big this difference is in comparison to the difference of those two. And again, the parallel trend assumption, which in words is, had the terrorist attack not happened, the trend in car theft would have been the same in areas without Jewish institutions and in areas with Jewish institutions. Very powerful way of establishing causality if you're willing to take this parallel trend assumption. Let me give you 5 to 10 minutes, see if you can discuss this together with any questions that you might have had from the course. And I'll just make a quick summary of what we have done and take any of your questions before we break for today. So see if you can discuss either this approach of finding causality or anything related to the course so far. Let me take some questions. What are your questions? Is everybody clear? Well, I mean, this difference in difference is a really clean way of establishing causation if you can convince yourself that there's parallel trends. You see it everywhere. If you have an idea on figuring stuff out with these different diff type approaches, it's actually quite powerful. Actually, given that we have a little bit of time, I just want to very briefly tell you about this idea with a very fancy name, but very easy way to understand without knowing a lot of statistics, which is called this regression discontinuity design. What this is it tries to figure out the causal effect of a particular event or a particular variable due to entirely random rules. Okay? And because there's random rules all around us, this regression discontinuity becomes very powerful. So what I want to talk about today, and very quickly show you, is the following. When do you get elected to represent the population in the democratic vote? When you get 50% or more, right? On that particular bit, right? If you think about that 50% or more, it's actually completely arbitrary. Okay? So you might want to ask the following question. How much more likely are you to get re-elected, right, if you are the incumbent, if you are the party that's already in there, as compared to the party which is not an incumbent? So what advantage does being in power give you? Well, that's a very difficult question. Like, how the hell do you answer that question? Sounds very difficult. And it is very difficult, right? But there is a way that you could answer that question in a very beautiful and very simple way. And it's to do the following. Go around to areas where the current incumbent just won by a little tiny margin. Meaning, they was just lucky, okay? If a couple of more voters had voted otherwise, they wouldn't have been in power. And then compare their likelihood to be re-elected with similar districts where they just lost marginally. Okay? Now that's a really beautiful technique. Note, it's actually very powerful. And the best way to kind of show this is to show you a little bit of the graph here, really. No, actually, let me just skip to this. Think of this as some sort of like probability of being re-elected, right? Now, if you got very few votes, right? If you got very few votes, of course your probability of being re-elected is going to be relatively small, right? Because you are in an area where you're not very popular. But if you're very close to this cutoff, right? Where if you're to the right of this cutoff, you won on the previous election. And if you're to the left of this cutoff, you lost on the previous election. I'll give you a second, okay? So this gap here in the data, which is kind of like very obvious when you see it that way. This gap in the data, which is very close to this, just for this margin of people here, tells you that increased in probability of being re-elected if you are an incumbent. Right? So you go to all of these areas where you just missed it by a little bit, you look at the probability of being re-elected, you look at these areas where you just won it by a little bit, and that probability is, you have that jump over in the two. And you can read a lot more about this. I really don't want to spend much more time on this, but I do want to tell you that there is very simple ways that are very creative on trying and establishing causality on things that don't require a huge amount of statistical sophistication. As a matter of fact, if someone is explaining you statistics and you don't understand them, be very cautious of those people, right? They should be able to explain what the assumptions are, what the gaps are in their assumptions, or potentially weak points.
Yeah. Does this model assume that it's the same exact people that are voting, that there are not new voters?
No. It doesn't need to assume that, right? Because across the different districts, these voters can change. Okay, so you're not making that assumption at all. You don't need that assumption at all. The only thing that you need is that there is nothing special about the 50%, right? That's the only thing that you need. You just need that these people that are here are fairly similar to these people that are here, with one exception. This guy's the incumbent, this guy's not the incumbent. And on all other characteristics, statistically speaking, they would be the same. So, what have we covered in the past 3 days that I think you should take with you? If you think about it, it's almost like a self-contained course in itself, these 3 days. The first day, we really tried to scrutinize data, and I want you to go with that idea that every time someone throws statistics at you, ask yourself, What is their agenda? Can they explain to you how they came up with that number? Is their sample representative to what you're trying to go to? If you ask those three questions or similar questions, you'll find out a lot about any statistics that anyone throws at you. Okay? Statistics are not God-given, they're collected by humans. So a very good point was made with police and crime. When you look at police and crime, you're looking at registered crime, right? You're not some sort of all-knowing God that can see through all the crimes, right? You just collect them, right? And those statistics, that's all you have. And they're going to be always imprecise and imperfect. The other important point that we made in that first lecture was correlation does not imply causation. So every time you see correlation, be very worried about immediately establishing causality. Okay? Especially if there's something that's important to you, like, do I send my kids to private school where I pay a lot of money, or do I send my kids to public school where I don't pay a lot of money? And what statistics is being provided to me, right, in order to make that decision? Okay? What statistic is being provided to me? By the way, I went to a private school as well, but I didn't know statistics in back then to argue different things. That was class 1. In class 2, we started to build up a little bit more about the tools that you need. Variances, covariances, how you calculate those variances and covariances. What is the normal distribution? Why is the normal distribution so important? We briefly talked about the central limit theorem and how everything kind of takes together. And don't forget the airplane and the World War II example. The sample that you get is usually biased, and you need to adjust for that bias. The planes that came back were the planes that survived the attacks. You need to incorporate that into your statistics. Okay? You need to incorporate it. Similarly as you need to incorporate the fact that where there is more police, there's going to be more registered crime. You need to incorporate that into your analysis. And today, what I try to do is give you the bare bones of hypothesis testing and tell you what are the different elements. In almost any single hypothesis testing that you're going to do, the elements are going to be exactly the same. You're going to have a test statistic or a variable that's going to help you make the decision. It's usually going to be quite obvious what that variable is. In the case of the machine, it's the average, intake or the average production of chocolate chips. The more challenging and the more technical bit is to go from I know what the statistics is to establishing a distribution for that statistic and then coming up with a rejection or acceptance rule depending on the tool, and you need a bit of training. And finally, we concluded with 3 applications, which were very easy applications that you could almost always do. Difference in differences, so be on the lookout for natural experiments that causes different things to change. The Jon Snow example in the police. And finally, be on the lookout for random rules. Right? For example, this regression discontinuity, you could also use it in scholarships. Imagine that there's a scholarship that you get if you get 180 on XYZ test. If you got 181, and someone got 179, and you get a lot of these people, the 181s and the 179s, so you get a lot of them. Well, one got a scholarship, the other didn't get a scholarship. So you might be able to answer questions like, how valuable is that scholarship to graduate, for example, for those people that are very close to that power. So you have various methods that you can establish causality. As managers, you're going to have work settings that you're going to have lots of random rules. You make the cut, you don't make the cut. Right? You get this computer, you don't get this computer. And then you can try and figure out the data to get to that. With that in mind, I will see you, I believe, on Monday, some of you, and on Tuesday, some others, and on Wednesday, some others, right? For the managerial economics classes, which start next week. So in those classes, I get to know you individually, so I'm really looking forward to that. Thanks for coming, and I will see you at 2 today, whomever comes, and on Monday, whomever doesn't come. Thank you.